Okay, folks, here we go. I'm back. Okay, so sometimes I might just have to cut off the lecture. Stuff happens, no big deal. I expect the same will probably happen to you. So let's pick up right where we left off with this significant figures. So hopefully you had time to review all this stuff. It's kind of a lengthy list, but I think it's better we learn it through application instead of just reading a bunch of definitions and rules. So let's move forward and do some examples, okay? So there's two operations, or two classes of operations we want to think of when counting significant figures. Multiplication and division, those both have the same rule, so I'm going to loop or combine them together, rather, okay? And I want to get rid of that. There we go. Okay, so when we do multiplication and division, it's all about the number of sig figs, right? We've got to count them up just like we said in the rule. And the number of sig figs in the final answer is the same as the number of sig figs in the least precise number. So what does that mean? Well, the least precise number is the number with the least amount of sig figs. So for example, if I take 10.2 times 1.4, and you do that in your calculator, you're going to get 14.28, okay? So if we count up those sig figs, right, we know that 0 is a captive 0, right? So there's 1, 2, 3 sig figs. Here in 1.4, there's no zeros, so 1 and 4 are always significant, so there's 2 sig figs. But now when we did this multiplication, we got 4 sig figs, right? 14.28 gives me 1, 2, 3, 4 sig figs. Well, remember, the number of sig figs in the final answer has to be the same as the number of sig figs in the least precise number. So the least precise number had 2 significant figures, so our final answer can only have 2 significant figures. And this is where we have to remember rounding and the rule of 5, right? So this 14.28, if I were to round it to 3 sig figs, it would be 14.3, so 8 is greater than 5, so that makes this go up to a 3. But now, in getting this 14.3 down to 2 sig figs, 3 is less than 5, so it rounds down just to 14. And not 14.0, because if I wrote 14.0, that would be 3 sig figs. So it's just 1, 4, 14. Okay, so here is another example. 100 times 0.0254, okay? So when you throw that into your calculator, you're going to get 2.54. However, look, how many sig figs are in each of these numbers, okay? Well, 0.0254 only has 3 because the leading zeros don't count. But this number 100 only has 1, okay? So technically this final answer, and if we go by my rule of 5, right, we can round it up. So this means this answer is only going to be 3. So we lost a lot of information there from this only having 1 sig fig. But now what if we wrote this as 100 points, or another way to write this would be 1.00 times 10 to the 2. Both of those would be the same way of writing 100, but with 3 significant digits. Then we'd have 3 and 3, so our answer would be 2.54, okay? So it helps to understand how to count what is significant from these rules and then use these math operations from there, okay? So what about addition and subtraction? Well, addition and subtraction make another group because they have the same rule. And so with addition and subtraction, it's the number of decimal places in the final answer is the same as the number of decimal places in the least precise number. So this is just a little bit different than the multiplication, okay? So for example, if I was adding 12.11 plus 18.0 plus 1.013, all right? Obviously these all have different sig figs, right? 12.11 is 4, 18.0 is 3, and 1.013 is 4. But with addition and subtraction, it's all about the decimal places. So the key here is to line these up, okay? And we can see what decimal place they have in common. And you notice here, they all have a tenths spot, right? That 18.0 doesn't have a 100th decimal place. So that means our final answer is only going to go to the tenths place, one decimal place, okay? So that's our rule with addition and subtraction. And I think if you want to line the numbers up like elementary school arithmetic, you know, line it up from top and down, line up the decimal place, that's a good strategy. That's perfectly okay to do, okay? So let's work through a few examples. And this time I'm just going to kind of like work our way through them together, okay? And so here, number A, we've got 6.022 times 10 to the 23. So that's one number. Times 1.05 times 10 to the 2. Okay? So now, how many sig figs do we have? Oops, sorry. I'm confusing myself even. So I should have put parentheses around this. So you should interpret this as 1.5 times 10 to the 2 times 6.022 times 10 to the 23. Okay. So here you can see I've got 1, 2, 3, 4 sig figs here and 3 sig figs here. So my final answer is going to have 3 sig figs. So when I plug that into the calculator, and don't forget to take advantage of that E button I show you guys, right? Let's do that one more time so you can see how I do the E button. Okay? So I'm going to say, 6.022. Do that capital double E, EE, 23 times 1.05, and I'm going to use that EE button again, which is the same as just saying times 10 to the power 2, and equals. Okay, so I get a whole bunch of digits in my calculator. 6.3231 times 10 to the 25. We recognize this should only have 3 significant digits, so it's going to be 6.32. 6.32. This extra 3 right here, it's less than 5, so it's not going to influence this 2 to round up. Okay? So that is 6.32 times 10 to the 25. Okay. So now let's do part B. And you can see part B here. Let me try to clarify that for you. That's 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8, all divided by 2.54 times 10 to the minus 9. So we have 3 sig figs from this number. We have 1, 2, 3, 4 sig figs from this number, and 1, 2, 3, 4 sig figs from this number. So our final answer is only going to have 3 sig figs. And I'm just going to give you the answer here. You should practice this on your calculator, pause the video, and make sure you get to the same value that I get. 7.82 times 10 to the minus 17 power. That's a times 10 to the minus 17 power. Let's make that look a little better, because I'm going to save all of this and export it. And you might be like, what the hell does that say? Okay, 6.82 times 10 to the minus 17. So now part C, look, this is a bunch of addition. And it's a bunch of addition with all of these scientific notation. And when you get to this, I take the advantage of like lining these up and writing these out as decimals. Okay, so 1.25 times 10 to the minus 2. So if I go 1, 2, that means I can write that as 0.01285. Okay, and then now 1.24 times 10 to the minus 3, I can go 1, 2, 3, and then that goes as 0.00124. And then now 1.879 times 10 to the minus 1, that just goes 1, and then that means it's 0.1879. And so now when I line all of these up and add them, okay, I've got 1, 2, 3, 4 decimal places, 1, 2, 3, 4, 5 decimal places, and 1, 2, 3, 4, 5 decimal places. It's that 4th decimal place. So the 8, the 2, and the 9. Okay, so when I add all of that up, my calculator gives me 0.20199, but I need to have 4 decimal places. 1, 2, 3, 4. There's the 4th decimal place. You can see that 5th decimal place is a 9, so that's going to cause me to round up this whole thing to 0.2020. Okay, let's box off the answers so we know later what the answers were, okay? So doing this addition and subtraction, take your time to line them up if you can't see it right away. Okay, so what about this letter D that has mixed operations, right? It has a subtraction and then a division. So we need to follow the order of operations in math, which says we're going to do the subtraction step first. So when I count these decimals, 1, 2, 3, 4, 5, and then here, 1, 2, 3, 4, 5, oh great, they both have the 5, so I can keep that. And when I do this subtraction on top, I'm going to get 0.00138. So we said 5 decimal places, 1, 2, 3, 4, 5, and then now divide by that 6.02205 times 10 to the 23. And now, because I'm doing division, it's no longer about the number of decimal places. It's all about the number of significant digits. So this number, 0.00138, while it has 5 decimal places, it only has 3 significant digits. And then this number down here, 1, 2, 3, 4, 5, 6 significant digits. 3 is the least number of sig figs, so 3 is going to be in our final answer. And when I go and do that math, I get 2.29 times 10 to the minus 27 with 1, 2, 3 significant digits. Okay? Okay, and then now finally we have another mixed case on the bottom here. We have a subtraction followed by a division, and then it says times 100, and it's telling us 100 is exact. And if you recall from these rules here, with exact numbers don't count, okay, towards sig figs. So if you know something is exact, like in this case, if this was maybe 100%, you're multiplying it by 100 to convert it to a percentage, then that's an exact number, and that doesn't count, okay? So if we go, here this has 1, 2, 3 decimal places, and this has 1, 2, 3 decimal places, okay? But you also notice that these are rather big numbers, right? So I'm going to rewrite that as, so times 10 to the 2, 1, 2, means that's 987.5 minus 1, 2, 979.5, all right? And so now you can see each of these has that 1 decimal place, so that's going to give me 8.0. That 0 counts because they both have that decimal in common. All right? And then now that's going to be 8.0 divided by 9.875 times 10 to the 2. And so now 1, 2 sig figs compared to 1, 2, 3, 4 sig figs, it's got to be 2 in the final answer. And of course, we know that this was times 100, but the 100 doesn't count. So I'm going to say 8.0 divided by 987.5, and I get, and then times 100, and I get 0.81. This is what my calculator says, and you can see it's 0.810, but that 0 is not going to influence the 1 to get rounded up. So that's the answer there, and this is the answer here. Okay? So those are some pretty good examples. Just a couple more slides to go, and we'll be done with this first week of lecture notes. All right, folks? So here we go. So let's talk about now why we have to think about significant digits, why they're important to us. And they're important to us because of the lab. Okay? It really helps us reflect the uncertainty in measurements, knowing how many digits are significant. So here's an example. So here we have a burette. Okay, and you're going to be learning how to use these virtually. I would love it if you learned how to use them in person, but c'est la vie. So here's a little picture of what this burette looks like. And it's got this little thing at the bottom with another little valve that you can open and close and allow liquid to drip out the bottom here, right? The liquid is going to go down. All of these lines that you see right here are called graduations. So for example, in a graduated cylinder, it has those little lines. A burette, a beaker, etc. Anything with those little lines, we call them graduations. And so when reading, in this case, a burette, this is different than reading a graduated cylinder, but reading a burette, because the liquid is dispensed down, you read the burette going down. So the first thing that's important to note is counting the graduations and what each value is worth. So here, let's see, here this big line is the 40, and then here this big line is the 41. So if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 10 graduations between the 40 and the 41. So that means each one of these is 0.1 milliliters. All right? And so when I'm reading this down, this is not a 42.1, 2, 3, 4, 5, 6, 7, 8. It's not 42.8. Rather, it's 41.12. Okay? And so now this little line right here, I'm going to draw my best possible attempt. That's what we call the meniscus. Meniscus, okay? And that's what we have to estimate. We have to estimate where that is. So the first thing that we do is write down all of the digits that we're certain of. So we know, for example, that it's 41 points. And then look, here's the 41.0, 41.1, and this line right here is 41.2, and this line right here is 41.1. So we know our result is going to be somewhere between the 0.1 and the 0.2. It's your job as the experimentalist to estimate what it is to the best of your ability. Okay? So if I were looking at this, where the meniscus is, I would say it's maybe closer to the 41.2 mark. So I might guess maybe 41.7. That's my guess, right? But there's no right or wrong answer because it's what we're estimating. So sorry, that's 41. Let me write that again. Not 41.7, but it's 41.17. Okay? So, and you'll learn this in lab as you go. But if our device has graduations every 0.1 milliliters, you're going to estimate the uncertain digit right here is one digit past the digit that you have a graduation for. So in this burette, you have graduations every 0.1 milliliters. That means you're going to have to estimate to the best of your ability the 100th place, the 0.01. I guessed 41.7. So let's say 5 people look at it and these are their results. Okay? Maybe one person thought 41.15, 41.18, etc. Well, we average all these together and we get 41.16, and we recognize that that 6 is the uncertain digit. And here we have 4 significant digits in this number, and that last one is always uncertain. All the same, the more digits we have, the more precise our number is. So that's why these burettes are very precise at delivering liquid. And I'm going to talk about what that means in the next slide. Okay? So precision versus accuracy. Okay? And again, instead of giving you a definition, let's learn by example. Which of the following is precise but not accurate? Okay? Well, we can talk about all of that for all of them. So A, you can see maybe this looks like how I would play darts after a couple of beers. So A is not accurate at all because we didn't hit the bullseye. And it's not precise. Excuse me, I got either a frog in my throat or recording 3 lectures in a row might be too much. We'll see. So, and it's not precise because these arrows are all over the place, right? If we try to average this result, the uncertainty would be large. But now if we look at B, B is not accurate because you didn't hit the bullseye. But it is precise because every single arrow went about in the same direction. Okay, and finally C is both accurate and precise. So yeah, good job, because not only do they all hit the bullseye, or they hit the bullseye and all of them hit the bullseye. So that's accurate and precise. Okay. And so hopefully you'll be able to explore this. Well, I should say hopefully. You will explore this a lot more in your virtual labs, this precision and accuracy and how we apply significant figures in the lab. So this will not be the last time you see a burette, and on these virtual labs, you're going to be able to like zoom in and look at the meniscus and make an estimate the same way you would in person, the same way you would in an actual chemistry lab. Okay, so I just want to talk very briefly about temperature scales. So here are the three temperature scales: Fahrenheit, Celsius, and Kelvin. And so you'll notice here the Kelvin scale is absolute. So there is such a thing as absolute zero. Insofar, we've never been able to get absolute zero. We've been able to get to a fraction of a Kelvin, I think about 1/1,000,000th of a Kelvin, but we've never actually been able to achieve absolute 0 Kelvin. We'll speak a lot more about what absolute 0 Kelvin means throughout the semester, but for now I just want you to recognize the Kelvin scale does have an absolute minimum bottom. You can't go any lower than that. The equivalent temperature of that in the Celsius scale is -273 Celsius. And the equivalent temperature of that on the Fahrenheit scale is -459. So when you say something is absolute zero, I think that sounds a lot better than like -459. Because why not -460 or -458, right? So this absolute zero makes the Kelvin scale much more universal, okay? So, and if you compare those numbers as we go through, you can see the things that are interesting to you. I mostly want to talk about then how you convert in the equations, all right? So if you think about this, if absolute 0 Kelvin is -273, then do a little algebra, right? And you'll find that you can convert Kelvin to Celsius by just saying the Celsius temperature plus 273, okay? And I've put this in a box, and I put this as a check mark because I want you to memorize this. I want you to know how to convert something to Kelvin from Celsius. So for example, if the Celsius temperature is 25, let's say 0.00, which we note as room temperature, even though 25 is kind of hot for room temperature, I think 20 or 21 is much more appropriate for room temperature, but scientifically we've defined 25.00 as room temp. So that means in Kelvin, and look at this, significant rules with addition, right? 25.00, 2 decimal places, plus 273.15, 2 decimal places, equals 298.15. But if I gave you like 25 degrees Celsius and asked you to convert it to Kelvin, then look, there's no decimal places, so that means it would only be 298 Kelvin, okay? Now, what about conversions from Fahrenheit to Celsius? You're gonna have to do a couple of these examples in your homework. I'm not gonna have you memorize these formulas, but I think it is useful to be able to convert. And mostly, since we know, we're typically programmed for the Fahrenheit temperature, right? recognize how to do this easily, like on a scientific calculator, right? So if it's 80 degrees today, which would be a very hot day in Humboldt, 80 degrees Fahrenheit minus 32, and then that's times 5/9. So times 5 divided by 9, that's 26.7. Okay, so what's 25 Celsius in Fahrenheit? Okay, so 25 Celsius in Fahrenheit, I can say 25, and I can say times 9 divided by 5 plus 32, and that's 77 Fahrenheit. That'd be kind of warm. That'd be a warm room if you were sitting in a 77-degree room. Okay, so be able to use these formulas. You don't have to memorize these two, but I do want you to memorize the Kelvin Celsius formula. Okay. Okay, so the very last thing we'll do for these week 1 slides, I'm going to give you here this sample calculation problem to work on. It's going to combine several of the things that we've talked about, unit analysis conversions, as well as significant figures. So this is a good problem to be able to work through. So let's read it, and I'll kind of describe my thought process as I'm going through this large problem. A material will float on the surface of a liquid if the material has a density less than that of the liquid. Okay, so back up and ask yourself, did you understand that sentence? A material will float on the surface of a liquid if the material has a density less than that of the liquid. Yes, okay. It's okay to back up and reread things if you have to. Given that the density of water is approximately 1.0 gram per milliliter, will a block of material having a volume of 1.2 times 10 to the 4th cubic inches and weighing 350 pounds float or sink when placed in a reservoir of water? It's a good question. My first impression is that it's going to sink. I mean, if I was just guessing, it's going to be a sinker for show, because it's like 350 pounds, right? That sounds like a lot. But we have to calculate it to find out, okay? So how do we even start? Well, what we need to know is, will the density be less than or greater than 1.0 grams per milliliter? So that's going to be our test. And so that means we're going to need to take the mass divided by the volume of that object and get it into grams and milliliters so that we can compare. Okay? So let's do the mass first. The mass equals 350 pounds, and I want to convert that into a gram. Okay? And the volume is 1.2 times 10 to the 4th cubic inches, and I want to convert that into a milliliter. And then finally, I'm going to divide those two things out and see if it's greater than or less than 1 gram per milliliter. Okay? So if we go to our unit cheat sheet, let's back up for a sec. Where is it? Okay, here we go. So we know, okay, very good, look. 1 pound is 0.4536 kilograms, which is the same as 453.6. So 1 pound is 453.6 grams. Okay, so here's how we're going to use that number. Okay, so I'm going to start with the number, right? Remember, in our conversion process, start with the number you have. So I'm going to start with 350 pounds. And I know, and I'm going to do that process, right, where I go down and then up. So I'm going to put pounds here and grams here because I know I have a direct conversion. That cheat sheet told me 1 pound is 453.6 grams, and that's all I got to do. Pounds and pounds cancels, and I'm left with grams. And when I go and do that calculation, think about our sig figs. Look, I've got 1, 2, 3, 4 sig figs, but only here I have 2, right? Because I don't have that decimal point. So that 0 doesn't count because I don't have that decimal point. So that's only 2 sig figs. So when I do that calculation, my calculator gives me 1.59 times 10 to the 5th grams. And so I know, well, actually, I probably got more digits than that. So let me see, 350 times 453.6. So this is what I get. 158760. Okay, so if I'm estimating, then I go 1, 2, 3, 4, 5. So 1.58760 times 10 to the 5th. I made it 1.59 with 3 sig figs, but you can see really with the 2 sig figs, it's only going to be 1.6 times 10 to the 5th grams. Okay. And now my volume, this is where this gets tricky. Okay, so I'm going to start with the number that I have. Start with what you have. 1.2 times 10 to the 4th inches cubed. And I'm going to do this process where I go down and up and down and up and down and up. So I know that I can put an inch here, and I need to get that to milliliters. And as a hint, remember, 1 milliliter is the same as 1 cubic centimeter. And the reason I'm pointing that as a hint, because check it out. On my cheat sheet that has the units, where is it? Oh, look at this. 1 inch equals exactly 2.54 centimeters. So when you see one of those things that says exactly, that means the significant figures don't count. So this is like not, these 3 sig figs here are not going to limit you. So 1 inch equals 2.54 centimeters. That's useful. Okay. And that's useful because I can say now, I know I can say in 1 inch, there's 2.54 centimeters, but I didn't get this to be cubed. So I got to cube the whole thing. Cube it. Okay? So not only, get out of there. So not only am I going to cube the units, but I'm also going to cube the number. Right? So when I go to do that calculation, that's going to be the same as saying 2.54 cubed centimeter cubed 1 cubed inches cubed. Okay? So that cancels out my cubic inches and my cubic inches. And then now I need to take 1.24 times 10 to the 4th times 2.54 cubed. Okay? And 2 significant digits from this number right here. Okay? And when I do that, I get, I'll just go ahead and do the estimate now. I get 2.0 times 10 to the 5th cubic centimeters, which I know is exactly the same 2.0 times 10 to the 5th milliliters. They're exactly the same. Okay. So now, finally, to calculate the density, Greek letter rho, it's going to be the mass, which was the 1.6 times 10 to the 5th grams, divided by the volume, 2.0 times 10 to the 5th milliliters. Okay, and when you plug that in your calculator, look, you're going to have 2 significant digits. I get 0.81 grams per milliliter. Uh-oh. I thought for sure this thing was going to sink. It's going to sink, remember, if it had a density greater than the 1.0 milliliters. But the density was 0.8, so that means it's definitely a floater. Okay, and that 350 pounds, right, that seems like deceiving, right? But its volume was significantly large enough that it would actually float on water. So maybe this thing was a boat, like a giant, heavy boat. Okay, so let's go to the learning goals, because that, for me, kills it for the slides. Okay, hey, how about that? Calculate the density of substance in any unit, given its mass and volume. We literally just did that, so I'll highlight that. That's awesome. Okay. Know the SI units discussed in class, how to enter, convert them, and how to apply scientific notation. We talked about that. Make sure that you feel good about that. Convert a quantity to another specified quantity through the process of dimensional analysis. So again, my process is to go down, up, down, up, down, up. Okay, we definitely did that. Apply significant figures in calculations and measurements. We talked about that. We talked about the difference between accuracy and precision. And then finally, be able to convert between Celsius and Kelvin. I didn't give you an example, but you can see it's a pretty straightforward formula. So we got through all my learning goals. I want you to make sure that you feel okay about these learning goals. So as you're going through and watching these lectures, and you feel like maybe we just covered a point here, then check off how you're feeling in these categories, right? When you first start, I don't expect that you're going to be ready to take the exam right away. You're probably all going to be in this category 3 when we start, and that's okay. That's why you're going to practice. Check out those question banks. Those are going to give you good opportunities for practice. And I'll speak more on those question banks during our discussion. Okay. So that's a wrap for week 1, folks. We are 1/16 of the way there. Hallelujah. Okay. I will see you folks live on our discussions. Hasta luego.